All right, so we looked at 4 possible scenarios for screws, and we found the relationship between moment that needs to be applied to the screw to keep it where it is or stop it from, let's say, going downward or upward, or stop it from moving in either direction. We found out the relationship between the moment, the radius of the screw, lead angle, the angle of a static friction. And now let's take a look at an example and see how can we actually use what we learned for real, I would say, world application. All right, so here we have a turnbuckle. Right, turnbuckle is a pretty simple device or mechanism. Some of you have seen it, or maybe a lot of you are familiar with what it is. Just to make sure that we all are on the same page, turnbuckle is a simple device. We use it to adjust the tension in ropes, rods, cables, and the way it works, basically, just briefly explain it. We have the main or the middle part, if you can identify this as the middle part. It is typically called a threaded eye bolt. It's just a piece of metal the way you see it. There are 2 holes on both ends, and those are threaded. Then we have 2 screws coming through. These 2 screws, one of them is right hand thread and the other one is left hand thread. So the way it works is when you turn this middle part or threaded eye bolt, I mean, let's say in this direction or the other direction, when you turn it, right, if you turn it in this direction that I showed, these 2 screws are going to start getting closer to each other because one of them is left hand thread and the other one is right hand thread or right hand threaded. And if I turn it the other way, these 2 screws are going to start getting farther from each other. So in that way, you can actually increase or decrease the tension in whatever is connected. If you think of it as a tension force, right? Tension force. You can increase or decrease tension in whatever is connected to this. Could be a rod, like in this case, or it could be a rope. Right? One simple application would be when you go out and you put together a tent. Maybe you have one of these turnbuckles to make sure that the cable is stretched enough to keep the tent in the way you actually want it, and nothing and the tent doesn't really it doesn't fall apart if there is some kind of wind or just by itself, if it's not tight enough. The ropes are not fixed the way they should be. All right, so that's the general story about turnbuckle. Now what we have here is a turnbuckle. It's single threaded. Right, the screws on both sides are single threaded. Now, everything we did was for a single threaded screw. Right, now, what happens if you have a double threaded screw? Well, all you need to do is that in all the equations we found, you just have to replace L, which was lead. Remember lead, hopefully you didn't forget that. You have to replace L with 2L if you have a double threaded screw. Right. In our case, it's just this in this scenario, it's a single threaded screw. So all the relationships we found, we're just going to use them the way we represented them. Let me just put write the statement or example statement there to say. It says the turnbuckle has a single threaded screw with a mean radius of 5 millimeters and a lead of 2 millimeters. if the coefficient of static friction is, let me be more precise, of a static friction between the screw and the turnbuckle, the turnbuckle is mu s 2.25, determine the moment m, right, that must be applied to draw the end screws closer together. And it's going to make redundant there, to draw the screws closer together. Now, also we're asked, is this a self-locking screw or not? All right. So a couple of pieces of information we're given. We know the lead L, we know the radius R, we know mu s, meaning that we can also find phi s, right? Phi s is basically tan inverse mu s, so that shouldn't be a problem. We can easily calculate that. Now, if let me show you the more schematic way. Let's go. Let's take a look at this. So I'm applying M, right, on this middle piece, which I told you was called the threaded eye bolt. Right? Apply M. These two screws, one on this side and one on this side, and we are also given these 2 kilonewtons. This is part of the problem statement. So I didn't provide that piece of information because I was going to show you this figure anyway. So this is we know the tension, right? 2 kilonewton on this side and 2 kilonewton on this side. What I want to do is I want to find out how much M is needed. What is the magnitude of M that these 2 screws, this one starts moving this way and this one starts moving this way. Right? Or both of them starts getting closer to each other. Now, how do we use what we learned from before? Let's take a look at what we know. We're talking about upward and downward. How do we match them to this case, which is really not clear? Are we downward, upward? Here's what you do. Look at what happens here. Right? In the upward impending motion, right, we are talking about the situation for which load is downward and the motion is about to happen in upward direction. So load, I'm talking about this case. So load, the direction of the load and the direction of the screw, that at this direction we want the screw to move, is in the opposite direction. So we want the screw, or the screw is about to move in the opposite direction of the load applied to the screw. If you look at the impending motion, downward impending motion, the load, the direction of the load and the direction of the motion are the same. Right? The load is downward, and also we are about to move downward. So that's going to be the key to determine which set of equations you have to use. If you go back to what you have here, look at those 2 kilonewton. These are your W's, right? This is W here, and this is also W. These are your force or loadings. Your loading is in one direction, and you want your screw to move in the opposite direction. So the directions are not the same. That's the hint that tells you have to look at the relationship you found for upward impending motion. Hopefully it makes sense. Right? So the direction between, or better to say, the directions of load and the possible motion are going to tell you which set of equations you have to use. In this case, they are in the opposite direction. As a result, you have to use the relationship you found for upward impending motion. So here is the equation that I have to use. M is equal to, what was that? M RW tan or W tan theta plus phi s. So that's the relationship equation that you need. You're given R, you know W is basically the load, which in this case is 2 kilonewton. You know phi s, you can actually calculate that. Let me write it here. Phi s would be tan inverse mu s. Basically, that means tan inverse 0.25. Theta, right? What was theta? Theta was lead angle. Let's take a look. Lead angle is, we found the relationship all the way here. Tan inverse L over 2 pi r. Now, this is a single threaded screw, so keep the L as L. If it was double threaded screw, you had to replace L with double. And that's actually something that you will see if you take a look at sample problem 8.6 in your textbook. All right. So in this case, it's single threaded, so tan inverse L over 2 pi r. We are given L is 2 millimeters. I'll keep everything in millimeter. R is 5, so that would be 2 pi times 5. I forgot the tan inverse part. So tan inverse 2 over 2 pi times 5. Right? That's how we calculate phi and theta. So in this equation here, you have pretty much everything. Now, where is the trick? Here is the something that you really have to be careful. We have 2 screws here. So you either have to write this twice, or we can easily just say, well, I have 2 screws. So the moment I need should be doubled, because remember, we are trying to push both of them towards each other. If you had just 1 screw, the first equation was sufficient. But this is because we have 2 screws, right? You need more moment to be able to push these 2 close to each other. If you just had 1, again, that relationship was good enough. All right. So let's plug things in. W is 2 kilonewton, R is 5 millimeters, phi s, I'll give you the value, and theta. So phi s, if you do this calculation, you're going to get 14.04 degrees, and theta, you're going to get 3.64 degrees, right? Lead angle. Knowing these, we can actually find M. M would be 2 times W is, let me write 2, actually, let me write everything in SI. 2000 times 5, let me go with the same order. R is 2, so that becomes meter times W is 2000 times 10 of theta 3.64 plus 14.04 degrees and degrees, and that'll give you m. That you will get m as 6374.7 Newton meter, since it's a moment. All right, so that would be the moment you need to get into the impending motion, the direction, in a situation that the load and the direction of the motion for the screw are in opposite direction. Now, the second part is this a self-locking screw or not? So to determine if it's a self-locking screw or not, you just have to look at the relationship between phi s and theta, right? In this case, obviously phi s is greater than theta. So we say since phi s is greater than theta, it's a self-locking screw. Remember, here's what we're talking about, self-locking screw. We said, well, if phi s is greater than or equal to theta, then we have a self-locking screw, meaning that if you remove m or moment, we are let's put it this way, the screw doesn't move. All right, so it's self-locking. Now, remember when I said 4 possible cases, now you see that these are not mutually exclusive. You can have a self-locking screw mechanism when meaning that when you remove the moment, it's self-locking, and when you apply the moment for upward impending motion, or you want to be in the upward impending motion, or you are in upward impending motion, you want to calculate use the relationship between parameters and the moment, you can use the relationship you derived for upward impending motion. So these are not mutually exclusive when I talk about possible cases, right? Exactly like the example we see. We have upward impending motion, and it's also self-locking, meaning that if you remove m, it's just going to stay where it is, which makes sense how it should be, right? That's if your turnbuckle is not that way, you have a problem, right? You can't just keep applying a moment there, or have a moment applied to your turnbuckle to keep it where it is. That's not a good turnbuckle, I would say. So few things. We had 2 screws, that's why I put that 2 there. You could just do it separately for each screw and then sum them up. The easy way would be just to multiply them, because both of them are in the same situation. They're all as we call that upward impending motion condition. It turns out that it's self-locking, which again it should be for a turnbuckle. It's expected. And one thing I mentioned is that this is, as the problem statement says, a single threaded screw, and just we use the relationship. So we use the relationship that we found, because all the relationships we found was for a single thread screw. Now, if you have a double threaded screw, and as I mentioned before, if you look at the sample problem 8.6 in your textbook, you will see that you have to actually replace L in those equations with 2L. So your lead would be twice, meaning that for every turn, your screw is going to advance 2L.